So the rest of the unit is going to be taking a look at properties that we haven't really seen in first year, expanding our understanding of gases. So the first one actually is something that we mentioned very briefly, and that is, what if I have a mixture of gases? So we know that each gas in a mixture is going to exert a pressure that is, number one, independent of what the other gases are doing, and number two, it's going to be proportional to its fraction of the total number of molecules present. Because remember, we've always said it doesn't matter how big the molecule is, it only matters how many you have. So if we have a lot of molecules but they're not all the same, does it matter? Absolutely not. So here's the idea of one of the ideas from Dalton's law. So if I have three separate gases, each in a identical sized container at various pressures, if I were to take all of these gases and combine them, the total pressure would be the sum of the three individual pressures, because now I have proportionally more molecules in the container. So again, it doesn't matter how big those molecules are, the pressure that they are going to exert is proportional to the percentage of the molecules that they are. So again, keeping those two ideas in mind, we can develop a couple of equations that show that. So the partial pressure, so P of A, the partial pressure is equal to the number of moles of A times R times the temperature of A times the volume of A. And you can say the same thing for B, and so on. We also now know that the total pressure is equal to the sum of the individual pressures. So they would be equal to all of these guys added up. This is really the important part that you want to remember, though. But putting this here gets us to the idea of this fraction. So if they're mixed in a container, what do you have? You have the same temperature, you have the same volume. The only thing that's different is the numbers of moles of each thing. So the total pressure is really equal to the total number of moles times RT over V. And we can go one step further and say that the partial pressure then is equal to the mole fraction, so the moles of the gas divided by the total moles times the total pressure. So that fraction we give as an X sub A. So the fraction of the total number of moles is equal to the moles of that particular gas divided by the total moles. So that's mole fraction. So rather than writing all this out, we're simply going to write this idea as the symbol in the equation. So here's an example. You've got a study that says we want to look at a synthetic atmosphere and its impact on plant growth. You see the percentages that it has. So if it's a percentage, we can say it's that many moles out of 100. So we want to know what the partial pressures of each of these gases are if the total pressure is 745 millimeters of mercury. So you come up with this idea: the partial pressure is equal to the mole fraction times the total pressure. So again, if it's a percentage, I can take 1.5 divided by 100 times the total pressure gives me the individual pressures of each of the three gases. Since you have most of the gases argon, most of the pressure is coming from argon, and CO2 makes up just a very small quantity. Now you can also do this as a true fraction. So out of 1, move the decimal place over, this would be 0.015 moles of CO2 out of 1, 0.18 and 0.805 out of 1 for these guys. Okay, so now what if you have this atmosphere under the conditions of 121 liters and a 295 Kelvin. How many moles of gas are you going to have? Well, I already know what the pressure of the gas for just what the partial pressure of the gas of oxygen is. So here's my P. I have my V, I have my T. What I don't have is my N. So I can just solve for that using the partial pressure. To use R, since it is ATMs, I got to convert millimeters of mercury into ATMs. I got my volume, I got my temperature, and I got R. So I wind up with the number of moles of oxygen gas. Okay, moving on to a couple other ideas. You know what? I'm going to quit here because I think I'm going to run out of time to do the next one. So this is a short one. We're going to stop it here and